Good afternoon. Too early for that, everyone. I hope you're all doing well. And we are having now the second lecture of control. Again, as I said last time, today only the first slot. We don't have the lecture in the afternoon. This is due to our Dienstbesprechung, which we are going to have in the afternoon. So we stick to that one. I recommend still doing the two MATLAB courses, which I recommended, to get some experience for that. So what did we do last time? Some introduction to control, right? So we learned where is control coming from, why do we need it, and also, what's the basic idea of a control loop? What's the difference to open loop control, which you did in the third and fourth semester, Steuerungstechnik, right? So we had this example with when you drive the car, where you have manual open loop control, where you drive with closed eyes and you open your eyes, you switch on your sensors, so to say. You basically drive manually with closed loop control. As we're engineers, we want to automate these processes, right? For you, mainly it's going to be aircraft, but can be cars, can be wind turbines, can be anything, can be electric circuits, whatever you like. Okay. Actually, I want to start out today with a short recap on how a control loop looks like, and then we're going to start the first major part of the lecture, which is actually dealing not with control, but dealing with system dynamics, right? So we need to understand how we actually can describe systems mathematically, and because we're going to use those then to design our controllers. Describing systems mathematically, basically, there's a lot what you already did in mechanics, electrical engineering, all the basic subjects you need to take when you start your course, right? So we will make use of all of this and kind of try to get everything in one toolbox. So for us, it will not matter what system it is, the physical background, but we want to describe and analyze it mathematically, no matter what it is. So anyway, but let's start from the beginning, and I'm going to switch over to OneNote. So in controls, not like in flight mechanics, I'm actually using OneNote to do calculation and stuff. So I'm going to start out with that one and show you what actually recap what a closed loop system actually is, right? So we talked about last time about a closed loop. So we said we have a system, right? Just name it system for now. Can be a car, can be an aircraft, or whatever you like. In this class, we're going to say our system is having one control input, right? So U is not a vector, it's basically a scalar, right? So obviously you can have system with a lot of inputs. So in this case, U would be a vector. When you drive your car, you definitely will think about having more than one control input. You have the gas pedal, you have the steering wheel, and so on, right? So for us in controls, we're going to stick to the fact that we have only one. And obviously, we also have many outputs when you drive the car, right? You have the speed, you have the position of your car, you have the sidewise position, you have, what else can you have? The engine throttle, the rotation speed of the engine, and so on. Anyway, in this class, we're going to stick to the example where we only have a single output, right? So for us, controlling the system will be a single output. So this is not, it's a little bit restrictive, but I would say like 80 to 90% of systems you will control can be handled like in this way. Aircraft cannot. So this is the bad news for aircraft engineers, because you know from yesterday that you have a coupling in the lateral axis. What I tried to convey you yesterday, when you try to fly a turn, you need the ailerons and the rudder to make a nice turn, right? So this does not hold. However, for controls, we're going to stick with that. Okay, so if we want to do automatic control, we have something in mind which we call reference, right? So let's say you have a car there. This is your car. Let's stick with the example with the car today. Let's say this is a car. What you put in your car is probably the gas pedal position if you drive it, yeah. And what you get out is the speed of the car. So this is not really putting speed in and getting speed out, right? This is really putting gas pedal position in and getting the velocity out. However, for you as engineer, if you want to design an automated driving system, you don't care about the gas pedal position, right? This should be done by the controller. What you have in mind here, so you are here, right? What you have in mind here is the speed. So you have in mind a desired output and not the desired gas pedal station position, right? Okay, so what do we need to do with this reference? Well, we want to compare it with the actual speed of our car, but we don't know the speed, right? This is why we need a sensor. So for our car, we can measure the speed and then we can feed it back. Whatever sensor you like here, right? So you put a speed sensor on a rotation sensor on the wheel, and then calculate the speed, whatever you want, right? Use a vane or pitot tube like we use in aircraft. So, okay. The important thing is here we need to subtract that. I'm going to put that in red because this is of crucial importance here. Okay. So now what we have here is the control error. Why is this the control error? Well, we have something in our mind here, the speed, and we have some speed which we actually have. So the difference, the error, is our reference, minus our actual one. And it's not the actual one. I'm going to do an indices M, right? Because we have a measurement here. You will see this in the first practical example that this is not always the same. Depends on the sensor, right? In a perfect world, it's the same, but usually your sensor will have also some effects. Okay, and now we have the controller, right? And I'm losing a little bit of space. So what the controller is doing, it takes this error and generates us, for example, the gas pedal position and what we would like to have, right? And then we have the actuator. For example, could be an electric motor. Actuator. And this actuator now performs from our desired gas pedal position from the controller. Now this actuator makes sure that this gas pedal position is achieved, right? Obviously, when you design such a system, you will not directly act on the gas pedal position, right? You will directly act on the engine. But I think it's more like illustrative if I explain it with the gas pedal position. Okay, so the important stuff here is what you have to, as a user, you are setting just the reference, right? And you're getting out, hopefully, the speed. You are basically decoupled from your gas pedal now. And you let the job for the gas pedal do the controller. And now, the important thing is, obviously, you should realize if I have a control error of 20 meters per second or 50 kilometers per second, I cannot say, okay, I now need 50 kilometers per hour gas pedal position, right? So all this conversion is hidden in our controller. How this error is transported to the gas pedal position, this is hidden in the controller mathematically, right? So we take the error, multiply it with something, and then what we get is the gas pedal position. So really be sure, this is the first kind of boundary I think for students which they have to take. What a controller is doing, it's taking some kind of variable with a certain unit and is producing another kind of parameter with a certain kind of unit. And these two units, they don't have nothing to do with nothing to do with each other, right? Because you can stick everything in the controller. So if you say, okay, let's say if we have an error of 20 meters per second in speed, we want to push the gas pedal 5 centimeters. Let's say, okay, we need to divide it by 4, right? So 20 over 4 is 5 centimeters. So if I know I don't like centimeters, I like more millimeters, so then we are not dividing it by 4, but through 0.4. So all these things can be hidden in this controller, right? It's just a matter of what the system takes in. So we are actually moving a little bit of a way, which makes actually our life easier, right? From that we always need to work with the same units, or with SI units. In controllers, for linear system, we don't care that much. But this, for students, is kind of usually a boundary they have to take to understand that it doesn't matter. You can hide everything in the controller. Why we can do that? Because the system is linear. But we're going to talk about that today. Okay, bottom line here, we know what a control loop looks like. We have a system, we have an actuator and sensor. These are two hardware tools, right? Parts, and they basically connect our digital to our physical world, right? So with the sensor, we measure a physical signal like the speed, and we get a digital signal. The controller takes a digital error signal and makes a digital signal. So we need to transform that back in the real world, and this is what the actuator is doing. Our electric motor can handle a digital signal, and it creates an actual movement of something, right? So we are kind of, a controller is connecting these two worlds. To be fair, it was not always like that, right? Like 50 years ago, all the controllers were also built with analog parts, right? With real parts. A controller was not simply a computer program. It was built on a platine with resistors and with condensators and so on, right? So there you had a direct connection. However, you still had to measure and actuate, but these actuator and sensors did not have AD and DA conversion, right? So you didn't need a digital signal there, or the other way around, right? This is what the digital world, or this is the burden the digital worlds bring us, that we need to convert, because we always work in reality, right? Hopefully, our car will drive, our airplane will fly, but we are controlling in the digital world. So there's this kind of line. Okay, for us it's important we have a system and we have the controller. And what we're going to do now is, obviously the lecture name is control systems, right? So you're going to learn how to design controllers. But what we're going to do first, deal with systems. Because control design, as I said last time, is basically a mathematical job. You're designing controller based on a mathematical description of your system, of your car, of your aircraft. To be able to do that, we need to talk about systems first, right? And the idea here is that we actually standardize systems so that we don't need to care too much if it's an aircraft, a car, a robot, or whatever you like. It will always look the same. And this is the important point here. For us, a system will always have an input U and an output Y. And I try to keep to that notation through the course, that you always immediately know after a couple of weeks, oh, U, that's the input. Y, that's the output of my system. R, that's my reference I would like to have, right? So obviously today I'm going to show you the connection between actual inputs and this U and Y, right? Because at the end of the day, it's still a physical system. My aircraft still has the elevator input. I'm just calling it U, while in flight mechanics, we call it delta or whatever you like, right? So this, I try to make things a little bit easier here. Hopefully we can do that. Okay, so we're going to start now with the lecture. One thing, yesterday, I went through my papers from last semester, and I figured that a couple of students had some questions, which I then concluded that there was something in English, in the English version of thing, was kind of misspelled, or not. It was okay, but it could be misleading if you interpret it that way. This is why I kind of made some tweaks this morning on the PDF files. So if you work on these PDF files digitally, I recommend you now to download the actual one, or if you did it in the last hour, it's fine. I think I updated it about 9. If you printed it out, it's not that of important, right? But I hope it's at the bottom line, it's going to help with understanding. So if you realize that there are some tweaks now which are different from your version you have, don't worry too much. It's still the same content. It's just formulated a little bit differently. Just if you, at the end of the semester, well, I know everyone is learning throughout the semester, but in case you start learning at the end of the semester, you know you have everything in the right form, in a more understandable form there. Because when we get the whole course there, you might. I realized that students jump back from the last to the first lecture and try to understand things, and I hope these tweaks will help you there. But okay, for today's understanding, it's not crucial. Okay, so let's kick it off. The next chapter, or the first actual chapter, is going to be mathematical descriptions of dynamic systems in the time domain. Right? To be honest, there are different approaches how you teach control. They are all make use of mass. That's the bad news. The good news is, the good news. The thing is, you can either start with time domain, we will learn about the frequency domain, but I think as mechanical engineers, aircraft engineers, we are so much used to the time domain, right? We like when we have functions of time. We like our speed is a function of time and not the frequency, right? And this is why I actually start with the time domain, with describing systems in the time domain, because you should realize that that's the thing you're used to. When you go into labs on a university, you're basically doing it in the time domain. And this is why actually I'm going to start in the time domain. I know especially Americans will not disagree because they start in the frequency domain, but it's even more abstract than it is already, I think. And this is why I try to do it this way. If you think at the end of the lecture in summer, if you say it's better otherwise, shoot me an email or give me some feedback on it. Okay, long talk. Now I'm going to start. Again, for those of you who were there yesterday, my voice didn't get any better. So I'm actually happy that we can stick to this one lecture today, but we'll see how it goes. Usually it works for 45 minutes and gets better. Okay, so let me start the presentation, and we're going to kick it off with some basic examples you should realize from the courses you have already taken. So I hope this gives you a nice introduction. Okay, so mathematical descriptions of dynamical systems in the time domain. And as you already see here on the right-hand side, we're going to use ODEs. We're going to use differential equations, and in our case, they will be actually very basic. They're going to be linear. They're going to be they will be ordinary. So we are not using any partial differential equations. So actually, getting to the basics. And a very famous, a very natural example is actually what every mechanical engineer or even aircraft engineer or automotive engineer is used to is this spring mass damper system, right? So I'm assuming here we have a mass, we have a spring, and we have a damper. And actually, I'm going to try to use this example quite often because it's so basic, but I think it's easy understandable. So you don't have to worry too much about the example, and you can focus on the content. Because we know if we want to have a description of that system, so note, we have the force here, right? So we have an external force acting on the system, and what we are interested is the position of this mass, right? So pretty basic here. So what we can say is that we can apply Newton's second law, which says our mass times the acceleration of the mass is the sum of all the forces, right? Okay. So what are the forces? So we can focus here on the horizontal direction. We don't care too much about the vertical one. So we don't. You can turn this around, right, by 90 degrees, but then you have to consider weight as well. So I made actually our life easier and just want to look at the horizontal movement and not about the vertical one. Okay. So if we say so. For our example, the sum of all the forces basically means that we have this external force, Ft. In this way, it's positive. And we have the spring force, right? If we move the mass to the right-hand side, our spring force will act against it, right? So we have minus C times, and you know, spring force is always depending on the position, right? So we need to multiply this by Y. And we also have this damper, and it's also acting against our movement. So if we move this mass to the right, the damping force will act to the left. So it's also going to be a minus, and you for sure know that this guy depends on the damping, on the damping, of course, but also on the velocity. So if we don't have any velocity, right, this guy here is 0. Okay, so, sorry. So how do we get to the solution y of t? So how do we finally get to know what the solution, what the position is, independence of u of t? And so what's u of t here, right? I said I'm going to use u of t as an input, so we're going to say this force is simply our u of t, right? So the solution to y of t for a given input is the solution of the inhomogeneous ordinary differential equation, right? So what does this equation make it inhomogeneous, right? In German, inhomogene Differentialgleichung. Where does this come from? Well, inhomogeneous just means that your input is not equal to 0. So let me get this straight. Why we are always going to deal with inhomogeneous equations here. Why? Because as an engineer, we want to have an input. We're going to design a car, we want to drive, right? We're going to design an aircraft, we want to fly. So there will be user inputs, right? So just homogeneous differential equations are not really of interest for us because we want to influence our system. This is the basic idea of designing systems, right? We're not just let it go. Even if you let it go like a satellite, you will have control inputs there. So you are able to influence that system. And this is why our system will always be described by inhomogeneous ODEs. So don't be confused about that. Okay, but how do we get there? How do we solve inhomogeneous solutions or ODEs? Well, we first solve for the homogeneous solution of the ODE, right? So we set our input to 0. So this now gives you the system response, how the system would react without any input. But as we have an input, we have to do this first. And secondly, we're going to shoot for the particulate solution, where we consider the inhomogeneous part, right? So we consider the input. So this is basically how you solve it on paper, right? You have learned this in math. How do we solve ODEs? We take the ODE. If it's inhomogeneous, we take the homogeneous part first, solve it. It's pretty, there are basically toolboxes for that, right? Take your mathematical formula, look through it. It will tell you how you solve it. And then if you have done that, you can tackle the inhomogeneous part. You calculate the particulate solution of your ODE, right? And this gives you overall the solution for y of t. Okay, so this is basically just a strategy to solve for y of t, right? If you do it numerically, you don't, on a computer program, you don't go for the homogeneous solution first. You directly solve it numerically, right? But obviously on paper, and we're going to do this once or twice on paper, you will see that this is a kind of well-known established mathematical approach to solve it because it gets actually straightforward. Okay. Again, this is more like I would like to convey you that this example is pretty simple, but it allows me to describe basic things, right? What a system is, it is described by this differential equation. We have the input u, in this case it's the force, we have the output y, here it's the position directly y, and we solve it by doing the homogeneous part first. So we set our ODE to 0, solve the first part, and then solve the particular part, and then just we simply add those things together. Okay, so let's take some other examples. So this was a classical mechanical examples, right? So let's talk about this water tank, right? Could be your bathtub, for example. So if you want to know how is the change, how is the height in this tub or in this mug changing when you have an inflow of water and you have some outflow. So this can run out here as well, right? So what you want to know is how is the height or the altitude changing over time, and this is the definition of simply um, um, building the derivative of h, right? So obviously we know there's an inflow, which, and we're going to define this one positive up, right? So you say if the height is increasing, we say it's going to be positive. Then there needs to be a sign, because if we lose some water, it's going to decrease. So is this everything? Is this the whole differential equation? No, because it also depends on our surface area, right? So if we make this bigger, the speed of altitude of height change is going to be slower, right? If we make it smaller, it's going to be faster. So we need to divide by 1 over a here. Let's take curved brackets. Okay, another differential equation. Okay, let's talk about this circuit here. So I'm just doing some examples where you should see. So the idea here is I just give you some intuition and some practice. To be honest, in controls we will not do system modeling, right? So I will not give you like a circuit or like this tub or like a mechanical system. You need to build the equation. You will already have the equations. But at this point, I want to convey to you that these equations are all differential equations, no matter in which area you're working, right? They all kind of look the same, and it makes sense to standardize our tools for that, because it doesn't matter if it's a mechanical or electric circuit, right? We can apply the same tools to analyze it. Okay, so what do we have? We have famous Kirchhoff's voltage law, which is simply kind of Newton's law, right? But it says for that circuit here, we simply need to sum up all the voltages and they need to be 0. Okay, so let's do this for our example. We have here, this is the input voltage. I'm going to write it down. And this is the output voltage, right? This guy here. And obviously you should see that the output voltage is basically the same as the voltage on this resistor here, right? Because this is basically your with these guys, you're measuring the voltage. Okay, so the sum needs to be, I have an input voltage, and what happens in the circuit needs to be equal that input voltage. So our voltage at the output needs to be summed with the voltage of the condensator, right? Okay, so what do we know? We know that we actually, for the, sorry, not the condensator, it's a capacitor. Did I say it? Is that the translation? I'm not sure. I'm gonna look that up. So anyway, so now we know that the voltage on this condensator, capacitor, I think it's not condensator, right? In English it's capacitor, is 1 over C times the integral of the current in the circuit, right? So we are basically just replacing the voltage in the capacitor by this guy here. This is basic EE engineering, right? So nothing special there. Okay. And now we said we are talking about differential equations. So now we kind of try to reformulate this whole thing into an differential equations. Also by Kirchhoff's laws, we know that the current in the whole loop is the same, right? Current in the loop is constant, right? This, right? So, and this current is nothing but, if you well, let's say let's do it from scratch. We know with Ohm's law that we have this voltage here on the resistor is nothing but U is R times our current, right? And the current is the same, right? It's the same current we have in the condensator. This is what Kirchhoff also tells us. Okay, so we simply can say that IC is equal UA over R. Okay, so now what we're going to do is we're going to differentiate this equation. Then we have E dot here. U E dot is UA dot. The integral actually gets away. And we're going to plug in what we have here. So let's take this guy and plug it in here. And we have UA over R, right? So get rid of this. And now what you should see is that you simply say, okay, we have an input. This input is UE. So let's call it U. We have an output, which we call Y. And here it's Y dot, of course. So we can write this whole thing in Y dot plus 1 over CR times Y, right? And now, again, you should not be surprised. It, again, looks pretty similar than the ODEs we already have, right? Now I already standardized it to U and Y. So I hope I can convey to you that this kind of linear ordinary differential equations show up at a lot of problems we have, right? Again, you don't need to do any modeling in this course. This was more like to show you that these guys show up. I will do some more modeling just to explain to you when we go through all the system types to give you a connections to what we have. But I hope this kind of helps you to understand what systems we are actually dealing with, because we're gonna abstract this whole thing and only talk about differential equations which have U and Y and derivatives of it in it. Right? But in the background, there's always like a physical system behind it, right? And this is the motivation for that. Okay. Okay. Sorry for that. So, as I said, differential equations arise for many technical problems by applying our basic knowledge, what we have learned in the courses, like in mechanics, in electrical engineering, in thermodynamics, for example, right? Any processes you have in thermodynamics are often also like linear, can be also described by these ODEs. Fluid dynamics, it's the same. Obviously, in fluid dynamics, you have partial differential equations. But if you usually do to be able to solve this partially differential equation, you actually make simplification, and often you also end up in these forms. So let's talk about. I know you're probably saying now, what is actually, he talks about linear, inhomogeneous, time invariant, ordinary equation. So what does this actually mean? At this point, I hope you saw that all the equations we tackled, and all three equations we tackled so far, had kind of this form here, right? We have inputs, which we usually put on the right-hand side, and we have outputs we put on the left-hand side. So this is important to remember, because we will this will come naturally, but yeah, I want to just say it at once. Okay, so what makes our system here linear, right? For me, I mean, this is basic maths, and probably a lot of people are going to say, okay, this is kind of boring, but really, we are only going to work with these equations if they're going to be linear, inhomogeneous, time invariant, and ordinary. And I want to talk about this once, and then it's set, right? So linear means that we don't have any terms like u squared here, right? So this guy n means just it's the nth derivative, right? A nonlinear one. So let's talk about nonlinear. You would, for example, have m2 dot to the power of 3, right? We only have first powers here, right? It's always to the power of 1. And this makes our equation linear. Same goes for you. And obviously also u times y would be nonlinear. We don't care about those, we only have linear versions of it. So you will always have separated u and y and derivatives of it. Okay, again, what makes our system inhomogeneous is the output, right? Inhomogeneous is we have an output here. Sorry, not the output. Obviously, we always have an output. We have inputs here. We are engineers. We care about our system. We want to influence our system. This is why we need inhomogeneous equations, because if they're just homogeneous, we cannot influence what's happening. We don't care about that system. Okay, time invariant. Let's probably take a different color. Time invariant. Why are our system time invariant? Well, they are time invariant, wrong green, because our system variables only depend on t, but not explicitly. They only depend implicitly on t. So what would be time variant? This is the opposite, right? So if you have something like y of t times t, or u of t times t to the power of 3, this is what we call time variant, right? So these guys here are all depending on t, right? I didn't put it there because the whole thing then gets too big. But obviously, you know that these are time-dependent variables. Otherwise, as an engineer, it doesn't make sense, right? When we talk about the car, we want to influence the speed over time, right? So it's depending on t. This is, yeah. Finally, they're ordinary. What's the opposite of ordinary? Partial, right? Fluid dynamics, you have partial differential equation where you take your fluid speed and build the derivative in every direction. So you have basically a function derivatives of dx, dy, dz. This is what you call a partial differential equation. Our differential equations are much easier. They are only ordinary because we only have derivatives of time, right? It's the only thing. So whenever you read y dot, y2 dot, they are y and u only derivatives of time, right? So d after dt, right? No derivatives in any direction. I need to restart the presentation for Shai because it's lagging, and lagging means usually there is some problem with YouTube, but a restart usually helps. Sorry for that. We'll see. Okay, so this is sorry. This is oh man. This is what the equations look like, what we are dealing with. So also, what as an engineer is relevant for us is the input-output behavior, right? So we have a system which is described by this ODE, and we want to influence it. Again, it's inhomogeneous, you want to influence it, and it has some output. But at the end of the day, most of the time we don't care much about y dot or u dot, right? What we care about is the input-output behavior, right? Obviously, this is not always true, but because if you buy a car and you say, okay, my input is the gas pedal position and the output is my speed, so y is the speed, you might care about y dot, right? Because if you want to have a huge y dot, you will pay more. Because if you have a better car, it has better in the sense of higher acceleration characteristics, you will care about y dot as well, right? But then you will define y dot or y2 dot or the acceleration as additional output, right? But this is a matter of freedom you have. You need to decide what you care about, at least on the output side. From the input side, it's more like design specific. If you design your aircraft, or you're a flight control engineer, you will usually get your aircraft and they're going to say, oh, it has 2 elevators, it has 4 ailerons, and so on, right? So, but they are there. But for the outputs, you have the freedom to think what you like. At the end of the day, what I'm trying to say is we need to solve this ODE to understand what the input-output behavior is, but it is this input-output behavior what we are interested, right? So this is the primary goal, and this is why we're actually gonna look at different systems and focus on an input-output behavior. Okay, and the good news is when you think now of an aircraft and you say, okay, I cannot describe an aircraft with one single ODE. Well, you could, right? But it's going to be a very large ODE. The good news here is that in engineering, we usually break our system down to a lot of subsystems. Yeah. If you listen to Professor Westenthaler, hydraulics, you're interested in actuators. And you know, actuators are in your aircraft. And there are plenty of those, probably 30 to 40 in an A380. So you can describe this single actuator by an ODE, and it's going to look pretty simple. If you take you take 40 ODEs, you already have like an ODE of 40th order just for the actuator in your aircraft. You're not going to do this. You will isolate this ODE and look at this one, right? But you have to understand that a complex system will have a lot of parts, obviously. And the same is true for the abstraction we are using in control engineering. You can use simple ODEs for each system and then we plug it together, right? But to understand, there's only a very limited subset of systems we need to understand because we know we can then just plug them all together, right? So this is, again, I think, good news. Okay, so this is why we're going to talk about some basic ODEs, and I think there are actually just 7 of those. Well, one is not really an ODE, so let's call it 5 to 6. And if we understand these 6 ODEs, we actually can make use of these 6 and understand every system, however complex it is. Okay. So, one more thing before we actually talk about systems and signals a little bit deeper. Okay, let's try to make this less abstract at this point. When you have a car or an aircraft or a robot, you as an engineer are interested in what do I put in, what do I get out. So we said this input-output behavior is important to us. Okay, so now the problem is I have an input which I like to test. Let's say you're gonna hop in your car and say, I'm gonna push full gas pedal, and I will see how the system is performing. Okay, you will get an answer for sure. But is this everything you need to know? Probably not, because sometimes you will not. When you drive in the city, you will probably not push your gas pedal to the very end, right? So what I'm trying to say is also if you drive on a mountain, right, it will be a trajectory of gas pedal position. So it's not always going to be full or nothing, right? You will make use of all the positions you have. What I try to get to is it seems to be very hard to talk about an input-output behavior of a system when you don't know what you put in, right? Because this input can be anything. You can, like, think of our aircraft here, right? You have more than one input. You can do crazy stuff here, right? On the pilot stick, on the engine throttle, whatever you like. So, is this a problem? The good news is no, this is not a problem because our system is linear. Because our system is linear, we can make use of very basic inputs because we know that if we want to test more complex signals, we can just compose these signals of these basic signals. And this only holds because of our system is linear, right? Linear means, and I will come to that now per definition, that if you put 5 in and you get 10 out, if you put 10 in, you will get 20 out. So it scales linearly, right? This is what a linear system is. This is obviously an approximation of the reality because you already realized that your car has a maximum position, right? So there's sometimes it's gonna stop, and it's not gonna be always like that in your car, right? If you get 50% throttle, you will get a certain speed, but if you get 100%, you will probably not get double because there's a saturation on speed as well because of the drag you have. However, we're going to make an approximation, and especially for aircraft, this approximation works pretty well, and we can assume that our systems are linear. Okay, let's go back to the slides. Before that, okay, as I said, well, this should, with all my talking today, this should kind of come naturally. Okay, so we said we're going to deal with scalar input output form, and this is what you're going to see very often. This is the so-called already introducing the block diagram algebra. We use signals as errors and we use system as blocks, right? So we send a signal in, like the gas pedal position. We have a system which could be our car, gas pedal, and we get the speed out, right? So these are signals. And this here are systems, right? And again, what you should realize, or I hope you realize at this point, the connection between your input and output is the differential equation. So the ordinary differential equations, or in German, Differentialgleichung, and with all the characteristics we talked about, right? So this is the connection here. Okay. But now let's talk about this linear, which I just tried to explain to you with words. Let's talk about this linearity, because this is a crucial thing, and really it's important to kind of get this idea today, because all the system, well, 99% of the systems we're dealing with are going to be linear. The only exception will be when we talk about a very basic controller. It's the bang-bang controller. It's non-linear. And we will have one session or one lecture where we talk about implementation issues, when you really want to take a controller to practice. There we will need nonlinear systems because obviously I just said systems in reality are nonlinear, but we're going to approximate those linearly. And this is why we need to understand today what linear is. And I will try to do it a little bit more. This is why it takes so long. Okay. So this is the definition which you can read in textbook. A system is called linear if the response to two or more linear superimposed input signals can equally be derived by the superposition of the input-output signals due to each input. And this is the superposition principle. Okay, so what does that even mean? So, okay, I will try to paint it out. So, a system is called linear, okay, if the response to two or more, well, forget this more, let's focus on the two for now, linear superimposed signals can be equally derived of the individual output signals due to each input. Okay, let's say, okay, we have a system G, and we have an input U1. And we put this input through our system. Think of the car again with the gas pedal position. And we get out an answer of our system. Okay, now we think of a second input. Whatever you like, right? And we measure the output. Obviously, we have now two different inputs and we have two different outputs. I mean, the output could still be the same, right? So, and what it says now, superimposed input signals can be equally derived by the superposition of the individual output signals. Okay, what it means is that alternatively we could say, okay, instead of doing 2 experiments, we're going to do 1, but we are superimposing them, the 2 signals, linearly. Superimposing linearly just means you can add these 2, right? So the point is you need to do this linearly. If you multiply them together, it's not going to be linear anymore. So we add our 2 test signals and feed it through our system. And then we get an output, right? And let's call this output Y3. And if the system is linear, Y3 is always going to be the summation of simply Y1 and Y2. Right? And this is pretty strong because we don't need to do this complex experiment on the right-hand side where we add all this crazy stuff here. We only need to do each signal independent, each experiment independently, and we know we can just add these 2 signals and still come to this signal Y3 here. This is all what the superposition principle says. But what's the consequence here? So what's the consequence for us now? Why do I bring this? Well, the consequence is that we don't need to take a look at very complex input signals, right? We don't need to say, okay, my U1 is going to be this one, right? We can say, okay, let's make U1 a simple signal like this, because I can construct this guy here out of a lot of these signals, for example, right? I can do U2, like this in the negative direction. And if I have a lot of these, I will end up with this guy by just adding them. But we can use this principle here to restrict ourselves to very basic input signals, right? We're just going to do this step, we're going to do an impulse, and we're going to take a sine wave and a ramp, and that's it. We don't need to cover every possible input signal because this would be impossible, right? We are making use of that signal, of this property of our system, and say we are just testing very basic signals because we know if we want to test something more complex, it's just going to be a composition of a lot of these basic signals to come up to that crazy signal there. Okay, that's the simple consequence. I don't need to show you a lot of signals, I'm going to show you 4, and that's it. And we're always going to use these 4 signals throughout the lecture. Bottom line. Okay, so let's talk about input signals then. Again, where are we at this point? We have a system, we have an input. And again, this is what we can decide. This is the ODE, and the output is the output, right? We get the output by solving the ODE. So we are mainly going to talk about input signals and ODEs, because if we have these 2, we can calculate the output. So, but first we talk about the input, then we talk about the ODEs, and for each ODE, we're going to take a look how the output looks like. And then we have a toolbox ready to do everything we need for every linear system, right? So this is the basic idea. Okay, so the first input, U, this guy here, I'm going to show you is a very basic one. It's the so-called impulse function, and it's really just an impulse, right? So here is the impulse function over time, and it looks like this. It's basically 0. Yeah, 0. It jumps up at t equals 0. Or let's be fair and say, okay, we've got some very small value epsilon here, minus epsilon epsilon, where the signal is not 0, and then it's 0 again. So if you would mathematically describe this, you would say, okay, my u of t is equal 0 if my t is bigger than some epsilon or smaller than some minus epsilon. And it's going to be some amplitude you like otherwise. So what would be an example for this? I know it's kind of hard at the beginning in controls to do this abstraction. Let's say this is our system. An impulse would be this, right? So I'm giving an impulse, and we see the reaction. This is probably nonlinear because it crashed. So it's probably not going to be describable with a linear ODE, but yeah, this is what an impulse looks like, right? So, and you can test a lot of systems on how the impulse response, the impulse response then is the answer to that impulse looks like. I'll give you I need to switch, right? I give you a sample response. Obviously, every physical system, if it's in equilibrium, needs to be 0 at this point, right? And then it could look like this. Right, this is just a sample. Obviously, the output here depends on how the system looks like. Okay, so this is the impulse. In MATLAB, there's actually, if you want to try MATLAB, there's the impulse function. It's really called impulse because it's so important. And it takes a unit step. So in MATLAB, U0, it's a unit impulse. It's always going to be 1. But you can scale it if you like. Okay, there's a special version of this impulse function, and I need to bring this, although I don't like to, because it's a little bit abstract. It's the so-called Dirac impulse. Okay, and this, we're going to need this guy later on when we go into the frequency and Laplace domain. But it's so important that it gets its own sign. It's the delta. And it's basically looks pretty similar to the one above. It's also 0. But we're going to say if t not equal 0, right? So it's always 0 except when t is equal 0. And it has a definition of an area. Area, you know, it's always defined by integrals, right? If you integrate it from minus infinity to infinity over this guy here, it's going to be 1. And there's now a problem, right? Because it's always 0, it's basically just something like this. And to have an area of 1, this guy needs to be infinite here. No, actually, yes, infinite here. Otherwise, yeah, correct. Wrong page I looked at. Okay, this is really just a mathematical description. If you want to test your system with an impulse in MATLAB, it will always apply a guy which is 1. But we will need this later on to understand some basic system dynamics, right? So I bring it here and that's it. Okay, even more important than the impulse is the step, right? So how does a step look like? It's also 0 for t smaller than 1, but it steps up or jumps, whatever you like, to a certain value, u0, right? So it's a continuous, and it's not continuous, it's actually discontinuous, but for t larger than 0, it's basically a constant, right? And this kind of makes sense, right? This kind of makes sense to test your system also with something constant. Why? Well, let's see. Well, this is probably not a good example because a constant input would just look like this, right? But you could say, okay, let's see what's happening if I have a constant input. Okay, it's jumping and then it's staying there. And this behavior we are actually seeing often. Think of your car. Start driving, you do a step, you push the gas pedal to a certain position, you figure out what speed you get at the end of the day. It will go from 0 to a certain value. And then it goes from 0 to a certain value, tells you already something about your system. So with a step response, I think this is the most important one of the inputs. You can already gather a lot of your system characteristics. Okay, so let's define it mathematically. Okay, so how does u of t look like? It's basically 0 if t is smaller than 0 and it's u0 otherwise. Okay, the example with the car could look like you push the gas pedal and it runs up to a certain value, right? Think of our spring mass temper system. This will probably oscillate. So this answer could also look like this, right? So again, the answer depends on the system. This is why this is just a sample. To make our life a little bit easier and don't, because we say we have linear systems, we can just stick and define the so-called unit step. It's pretty easy. It's the same thing as above, only that the amplitude is 1 here, right? So the consequence is that we can define each or every other step input with this unit step, because this guy here, it's just a scaled version of this guy. So we can plug out the amplitude. Okay, so let me get this straight. Why we actually, most of the time we're going to use a unit step. And actually this is true. We have a linear system, and this is what I tried to convey you before. If I put in my system 5, I get out 10. If I put in 10, I get out 20. So there's a constant factor in between. So if we know 1, we know all of the answers, right, to a step. So we basically can just take 1, we put a 1 in, we get the factor directly out, which kind of corresponds to this, the gain, what it's called, right? So this is why, bottom line, you can stick to a single one. And most of the time you do a unit step input. Obviously, it's if you have a system where you say a very large input is already 0.01, well, you can do a input of 1 if the system linear and scale it down, or you scale down the input first, right? It's linear, you can do what you want. So this is really the nice part. Okay, so these two, I'd say the step input is the most important one, closely followed by the impulse input or the impulse function, and I'm going to show you 2 more, but they're going to be summarized on one single slide. So the first input is the ramp function. It looks like this, and then it goes up with a constant increasing. So this guy here is constant, right? And the answer could be something like this, for example, right? So how does it look like? It's basically u of t is, again, for t equal t smaller than 0, it's equal 0. As engineers, we don't care much about the past, so this guy always holds here. And then we have an input amplitude, but this time it's multiplied by t, right? So we get this basically is this constant here on the input, but you need to multiply it by t. This gives you a so-called ramp. Okay, the other one is the sine wave, or the sine input, which gives you the sine response. This will be especially important later on when we move to the Laplace and frequency domain. Okay, now let's try. I try to draw a sine input. Okay, not that bad this time. So u of t is, again, 0 for t equals 0. This, by the way, should be otherwise, of course. And here we have a sine wave. It has a certain frequency, which we can define. And we can obviously also define the amplitude here, right? And this guy here is constant. So here you also can do unit or uniformed ones where you say, okay, my u0 is 1 for both cases, but that they are not so important that they don't get a special version. Okay, here the answer could be, well, it could be, the thing is, this is actually pretty important, but we will come back to that later. A linear system always responds to a sine wave with a certain frequency with a sine wave with the same frequency. And this is actually pretty important when we move to the Bode diagram, which you probably might have heard in electrical engineering already. So a harmonic input signal always results in a harmonic output signal with change amplitude and phase. Okay, what does that actually mean? Okay, we say our input is this guy, and our output is always also going to be a sine wave with a certain frequency. However, what's changing is the only thing what can change is the amplitude, right? And now I'm running out of space, and some phase shift. The important one here is the frequency does not change. So you can have here a different amplitude and you can have a phase shift, but the frequency does not change. So let's note this down. Frequency remains the same. Again, this only holds if your system is linear. Okay. Sorry for that. So on the next slide, this is the last slide, and this is the slide actually where I tweaked around a little bit last night, but you can just replace that slide in the PDF if you printed it out, or if you work on it digital, it should be easier anyway. The content is the same. It's really just getting the wording a little bit better and clearer, because I figured there was some misunderstanding in the last 2 semesters about that. Okay. So now next we covered the inputs, that's it, right? We have these 4 inputs and we can live with these 4. That's enough for us. Next, we're going to talk about the systems, and I'm going to do the classification of the systems already at this point, but you will probably understand it when we went through the system and I bring that up again at the end, right? But I think mathematically it's kind of comes quite naturally. Okay. When we talk about systems, we are mainly talking about 3 classes of systems. And why we talk about systems and behaviors and kind of use them the same way, I'll talk about that in a second. But let me get with this first. We talk about proportional systems, we talk about integrating system and differentiating system. And here it's really important for you, the systems, at the end of the day, they are ODEs. They are mathematical description of your hardware. If the system is acting proportional, integrating, differentiating, or any combination of those, it's really what it means. It's really integrating your input or differentiating your input. So always think about that when we're going to do the examples, because from my experience, students think too much about how the system is integrating. What does it actually mean? Well, it's integrating. This is bottom line. It's integrating or differentiating something. Okay. For short notations, we're going to use this here. If it's proportional, we're going to say P. If it has some lag or delay, we're going to use these guys here. What this all means is standing in here. So the important thing is, if it is proportional, integrating, or differentiating, just depends on how the input is processed to the output. And there I tweaked a little bit the sentence and try to make this clearer, right? So our input might be integrated, then it's an integrating system. It might be differentiated, then it's a differentiating system. It also can be any combination of these two. The famous PID controller actually takes your input signal, differentiates it, integrates it, and has a proportional term. Then it's a PID, right? So I indicates the integration and D indicates the differentiation. So this is this one set of 3 possibilities you have which are acting on your input. The other stuff, this T here, these are the same for all 3 types of systems, right? This T introduces some delay, some lag. So I replaced all the delays to lag, because in English we can do that. In German, unfortunately, it's always Verzögerung. But I think it's more appropriate to use lag here, right? And I will show you with the first example where we have a derivative, where we have such a T1 system, what it actually means. It basically means that you have derivatives of your output signal, and they actually cause some lag in your system, right? On the output. Okay, that's basically it at this point. Why do we use the terms behavior and systems? And this is kind of what I also tweaked yesterday. I have a system, right? And this system has, as we said, has an input and has an output. This is what we call system. But this system has these subsystems or sub-behaviors, right? So a system can include a PD1, an IT1, whatever you like, a D term, right? In this case, we would not talk about systems, but we would talk about behaviors. So a very complex system can be made up a lot of different behaviors, right? Because the system is linear, we're going to only learn 5 to 6 basic behaviors which we're going to build our systems with. So don't be confused here. I'm going to use, honestly, I'm going to use always systems. There's the small difference there that a behavior doesn't always need to be a system, because if you have like a complex system, you will decompose it in different behaviors because it will make your life easier. So then these decomposed parts are not all systems. They are just like behaviors in your system, right? So, but that's it for that, right? I'm not going to go into much detail, but if you read literature, sometimes they talk about systems, sometimes they talk about behavior. In German, it's even worse, right? They're never going to use the wording system. It's Glied, it's PD1 Glied, PT1 Glied, PT2 Glied und so weiter. Und das gleiche mit PT1 Verhalten, ja, das ist dasselbe. But if you talk about the system, you can use system, because as an engineer, you're more interested about system, right? An aircraft system, a car system. This is why I think it's more appropriate to actually talk about system and not behaviors or whatever, because at the end of the day, you're working on a real system. But yeah, to make everyone happy and understand when you read a book that it might have a different name. Okay. So let's talk about systems then. We're going to start off with proportional system, and probably we get to PD1 systems today. And I'm going to show you proportional system. I'm quite sure you already know. You just never heard it in the context of that's a system. But it's, yeah, I think it's pretty straightforward. It's only one slide. So let's talk about proportional systems. It's basically a constant factor. Okay, so the most basic system you can think of is the proportional system. So your output is only proportionally depending on your input, right? So when you want to know your output, multiply it with that constant gain, you get the input, right? So really pretty straightforward. Here I always show you the block diagrams first to get a little bit used to this block diagram algebra, and if you read books, sometimes it's really written there in that way. I'm not gonna discuss that much, but yeah, for the sake of complicity, it's there. Okay, if you, and these are now MATLAB examples, right? And here I actually did a step input, right? You see, MATLAB usually gives you times larger than 0. As I said, you can simulate times lower than 0, so minus times as well, but we want to stick to times larger or equal than 0. So this is now a step input, right? So this gray line here actually jumps to 1 here, and MATLAB then solves the output. And here you have a gain of 3, and you should realize from here that your y is basically 3 times your input. The input is 1, right? You see that here, the output is 3, right? In between, you could read out this gain, what we call here, right? This constant gain. This is what's standing here. So why is this important? Well, if I show you an output which is 6, and I tell you the input is 2, you should come to the same gain, right? Because I said the systems are linear. You put in the double that much, you will get out double that much, right? So, okay, let's talk about some physical examples. A gear ratio can be approximated with a proportional system, right? So, the rotation speed here of the output is simply the number of the T's here, or the ratio of the number of the T's times the speed on the input. This is a proportional system. There's no time delay there, right? A spring is a proportional system, right? I mean, you could write here y is kp times u, right? So this As I said, I will try U and Y most of the time, but I also try to give some physical examples. A spring force, right? The force is the output. The input is your deflection. You deflect that spring, you will get out a force, right? So Kp, this factor here, is basically your spring constant. Here, it's the ratio of the teasing, right? So pretty simple. However, this gain will stick around for a long time because now we're going to talk about proportional systems with lag. If you have an old version of the script, it's still delay, but please, I will going to use lag because I think it's the better expression. And when you go back one slide or two slides, I said, okay, the introduced lag only is defined by the derivatives of y, right? So y dot, y2 dot, y3 dot. So the only thing we're going to talk about for the proportional system now is adding something here. So we will have y2 dot, y2 dot, y3 dot, and so on. And this is why a proportional system on the right-hand side always has something which acts proportional on our input, right? So we take the input, we multiply it by a constant factor. As soon as you have this, it's going to be a proportional part in your system, right? Okay. So 10 minutes left. We're going to start out with a proportional system with a first order lag, or so-called PD1 system. So it's proportional, right? Meaning we have Kp times U here, and it's a first order lag. We already know we need to have not only y, but also y dot. This is why it's called first order. We have y dot here. Okay, but let's talk about it. Okay, so why it's called that the system has lag? Well, the system has lag because it's not immediately there, right? So if you look at the response of a proportional system, there is no lag. As soon as you jump to the 1, the output also jumps to 3, right? So there's no lag. Keine Verzögerung. It's immediately there. Okay, this time it's not going to be immediately there, but there will be some lag. And this lag is introduced by this y dot here. Okay, let's do t plus 1. So this is the left-hand side of the proportional system with the first order lag. We now have this y dot here. Okay, on the right-hand side, it's still proportional, right? So we still have Kp times U dot. So our input U is transferred proportionally to the output. So a lot of confusion, or a lot of, I think, what I figured is that, okay, now we have y dot, right? We have a derivative. Why do the heck we get slower, right? A derivative means we are actually getting faster because we are not looking at the signal, but we are looking at the derivative of it. So the speed, why are we getting slower? Okay, let me show you something. So what are we interested in? We are interested in y of t, right? This is what we want to know. Okay, let's take this equation without solving the ODE. Just take Kp times U of t. This would be now a proportional system, right? However, now we are subtracting the speed of our output signal. So this is where the delay comes from, because we're taking the change in the output signal and actually subtracting it from itself, from the output signal. And this is why we need a little bit more time to get there. So I hope this kind of gives you a little bit intuition where this lag actually comes from. Okay, block diagrams, you name it. More importantly is the how does the step response look like? Okay, I've plotted you an example. I kept Kp equals 3. I did a unit step, so U is equal 1 for the step input. And I set the time constant to 1. So why is this guy even called time constant? Well, it tells you something how fast the system reacts. It tells you something about the time it needs to change to the value you want. So, and this can be really, this parameter can be, you can really think a little bit about seconds. I'll show you in the plot immediately, but just see here, if you make t bigger, so let's say t is 1, but we make it 10, then we subtract it even more, right? So the bigger t is, the bigger the time delay is, because we're subtracting here more from our output. So we need more time to get there. Okay. So what do we see here? And here you actually see what happens, right? Instead of the output y being immediately at equal to the input, which is 1. So the input here is not, this is the input. We need some time to go up. If you put in the tangent here, you realized that this is exactly the time constant. So there are two ways to get to this tangent, to this time constant, right? You can look at this response. You go, you put in the tangent, and where the tangent cuts the final value, in this case 3, you look at the x-axis, there's your time. Or if you like more the calculation side, you know that at 63% of the output, there will be the time constant. Meaning that the time constant, this guy here, for a PT1 system tells you how much time you need that the output reaches 63% of the final value, right? Okay, so let's kind of write that down, what we just learned. Okay, so stationary, and this is important, right? We're still having a proportional system. So if you disregard all here on the left where we need this time, on this side it basically looks like a proportional system, right? So when we reach that point here, it actually looks like a proportional system. That means if we just wait long enough, so we let our time go to infinity, the system will look like a proportional system. There will be no y dot here, right? So that's why we can say if we do an experiment and our system looks like a PD1, we can just take our final value divided by our input and calculate our gain, right? Then I said, okay, reaching 63% of the stationary response happens exactly after this time constant. Okay, mathematically this means y of t is nothing but 63% of, so what's the stationary response? Obviously y of t, but y of t is kp times u0. Well, there's another expression for this. T is equal 63%. We're not going to use that terminology often, but just to make sure that you have seen it. Okay, and interestingly, okay, 63% looks like a weird number, right? So what does 63% mean, right? It's somewhere in the middle. So the interesting part is the so-called settling time, and we're going to use this for a lot of systems, is when you reach 95% of your final response. So it's probably going to be somewhere here. And this is quite important, because 95%, you're close to 100, right? So, and you reach 95% exactly after 3 times this time constant. So, same thing as above, kp times u0. So we call that 3t equal t 95%, or you also will reach the so-called settling time. T set. Okay. One side note, if you look here, a PD1 system has an initial gradient, right? So y dot of t equals 0 is not 0. And this is a specialty for the PD1 system. All higher order systems, PD2, PD3, PD4, have and don't have an initial gradient. Okay, so to close today's lecture, we're going to do the examples next time by the following idea. Oh, where's my mouse? What you want to do is, you have two possibilities. I said at the beginning of the lecture, we need a model of our system to design a controller, right? So this is where we want to get to. We want to have these equations. We want to know the parameter t numerically and our kp numerically. We want to know how the system looks like and have the equation there so we can design a controller. But the question now is, how do we get to this equation? Well, you have two possibilities now. We're going to do both, obviously. The first one is, you take all the knowledge you have from your courses before and say, okay, I'm going to model my system with for example, with Newton's law. And you do that, and you know the parameters, you know your spring constant from the manufacturer, and so on. You come up with this PD1 system. You have the equation there, set. You're ready to design a controller. The other possibility, and this is what we're going to do in the first practical exam, I'm probably going to upload it next week, is, no, we say we don't want to actually do this modeling from scratch, but we have our system here. We will do an espresso machine. I have one there. So you take this espresso machine and you do an experiment. How does this experiment look like? Well, let's put in a step input, right? So, and then you record your output. So you have the input, you have the output. And we know from today that in between there's the ODE. And now you have to do two things. It's the other way around, right? You look at the output and say, oh, that output looks like a PD1 system. I know how a PD1 system looks like. It's T times V dot plus T times Y dot plus Y equal KP times U. You write this down. The problem now is, when you did the modeling from scratch, you got the values from the manufacturer. So where do you get your parameters now from, right? The values for T and KP. Well, you know that 95% is reached after 3 times this T, or 63% is reached after 3 times this T. So you just take the output, what you measured, look at it, and calculate from that experiment your time constant and your gain. So these are two fundamental different ways, right? Doing the modeling, the mathematical modeling from what we have learned from basic equations, from basic physics, or take this hardware part and do an experiment, and they all should end up in the same differential equations, right? This should be the takeaway why I'm going to present you PD1, PD2, and then more integrating differentiating systems via step responses and via the ODEs. But in the background, you should understand that how to get to this ODE, there are two ways. Either I'll take a look at my plot, decide, okay, that looks like a PD1. Now let's try to identify the parameters, or you do the modeling from scratch and you end up at the ODE. Okay, so much for PD1. I'm going to switch over because there's one more thing, and this is what I just said, right? You can come from the basic equations, or you can do an experiment. Next time, we're going to look a little bit closer in some more PD1 examples, and we're going to solve probably. We're going to solve an ODE, first order ODE for a PD1 system only once, so that you already see what I mean when I talk about this homogeneous solution and the particulate solution. You probably have done this anyway in your math courses, but a little bit of recapture is always good. Okay, thanks for listening. As always, stay safe. Bye-bye.